Okay, everybody, let's try out this example, water jet. So, a water jet that leaves a nozzle at 110 meters per second at a flow rate of 120 kilograms per second is to be used to generate power by striking the buckets located in the perimeter of a wheel. That'd be great if I had a picture of this or something. Oh, I do have a picture of it. Nice. Now, let's determine the power generation potential of this water jet. Okay. Let's see, things I've got here, I've got a velocity for the water. I've got a mass flow rate. Both of those things are probably going to be pretty important. Now, let's figure out here and first think of what kind of energy is available. If I'm looking at this, I don't see in this any changes of height anywhere. It doesn't mention temperature. So temperature would be internal energy, so we're not having that. Potential energy would be if there was some sort of height change. I don't have that. So all that's left here is kinetic energy. Kinetic energy is what I have available to me. Now, with that in mind, what's our equation for kinetic energy? Well, we had this guy right here. Mass times velocity squared over 2. Okay, but wait a second. Oh, I'm looking at this. I don't see mass. I see mass flow rate. So this guy right here, m dot, would be equal to 120 kilograms per second. Now, you could, if you wanted to, define some arbitrary time and figure out the kinetic energy, but it doesn't matter because it said what is the power generation, and power is energy over time. Well, if I have mass over time, that's equal to m dot. So I'm still good here. So even though we have a mass flow rate and not a mass, we can still solve this problem. Now, our kinetic energy per unit mass is just v squared over 2. So we're going to do this, and we're going to multiply it by our mass flow rate to get the power generation. So I plug that in there. I get 110 meters per second. I square that and divide by 2. Now, this guy right here, this is a conversion. It's one you're going to see a whole awful lot when it comes to kinetic energy. It's converting from kilojoules per kilogram, which is what we wanted in energy per unit mass, from meters squared per second squared. And before you ask, yes, they actually are equivalent units. Just 1,000 meters squared per second squared equals 1 kilojoule per kilogram. That's the glory of the metric system. And so I get 6.05 kilojoules per kilogram. Now, if I know how much energy I can get from each kilogram of water, and I know how much water I have coming through, I can figure out the power. So the last step is going to be to figure out that power. So the dot right here, that is saying that this is happening over time. Same as there, same as there. That's always saying there's some sort of time frame. So I take my energy per unit mass, I multiply it by my mass flow rate, and that will give me kilowatts. Technically, you'll have kilojoules per second, but a joule per second is equal to a watt, and so that's why it becomes kilowatts. And that is our answer. Happy days, we've got it. So just going through this one more time, we had kinetic energy because it gave us a velocity up here. Since it gave us a mass flow rate, we had to calculate the kinetic energy per unit mass, which is why we use this equation. And by multiplying our mass flow rate by our kinetic energy per unit mass, we were able to get our power output. And this is a maximum. In real life, you would not be able to get 100% of this energy out of it. It would not be perfectly efficient, but it's still pretty cool regardless. Okay, that's it for this example. I know it's a pretty short video. Thank you for watching, and I'll see you all next time. Bye-bye.